All right. Well, thank you everybody for coming. It's great to see such a large turnout. My name is James McNellis. I work for Microsoft on the Visual C++ team. I work on our runtime libraries, but I'm here to talk today about resumable functions. Actually, that's a lie. I'm not going to talk about resumable functions today. I'm going to talk about C++ coroutines. Apparently, shortly after I sent Jens my proposal for giving this talk, it was decided to stop referring to them as resumable functions and just start referring to them as coroutines as they're advancing in the standardization process. So how many people here are familiar with the C++ coroutines proposal? All right, a handful of people. That's pretty good. All right, so just a few notes before we begin. This feature is still in development. It's not finalized. It's not complete yet. It is being proposed for standardization, but it's not standardized yet. As of the last meeting, I believe, there's actually now proposed wording for integrating it into the C++ language standard. So it's getting very close, but it's not finished yet. This presentation covers the current state of the proposal, which does not match any implementation today, largely because, so in the Visual C++ implementation with which I'm most familiar, we shipped an update very recently, but the C++ coroutines proposal had some modifications between when we finished that and when we actually ship. So some of the keywords have changed names. The extensibility model has been tweaked a bit, but overall this is a general view of the current state. You may need to tweak some things if you want to actually try them out with your compiler that you have today. I know that both Clang and Visual C++ are actively working on implementing this new feature. I don't actually know about other compilers at this time. All right, so with that out of the way, let's talk about motivation. Why are we thinking of adding coroutines at all? Right? Like if we're going to add something to the programming language, we actually need to have a good reason for doing so. Otherwise, we're just introducing additional complexity for no gain. And this example that we're going to look at comes from my colleague Gornichanov's talk at CPPCon 2015, so earlier this year. So thank you to him for providing this example. So here we have a function, and this is a purely synchronous function. This is code that we might write today. And basically, it's just going to open up a TCP connection. And when that connection is established, it'll continue on. And then it's going to, in a loop, try and read bytes from it into a buffer, and we'd probably actually be, doing something with those bytes in this program. But here we're only focusing on these, these long-running operations, right? So each iteration through the loop, we're going to read another buffer's worth of data. We're going to process it, and then when we're done, we're going to return either how many bytes, more than were requested that we processed, or how many bytes fewer. So, I mean, the obvious problem with this is that it's synchronous, right? So maybe that read from the TCP socket is going to block for a long time, and we don't really want to block an entire thread, waiting for some TCP operation to complete. So we'd really like to turn this into something asynchronous, where we don't block the thread, but the operating system calls us back and lets us know, hey, you've got more data available to process, and so now go and do that, and then you can return the thread back to the operating system thread pool or whatever between when you're not actually doing work. So let's try and turn this into an asynchronous program. I guarantee it'll be just as simple as this. So first, we're going to need to change the declaration of the function so that it returns a future of int64t instead of just an int64t. Because when this function returns, it's not actually going to have all of the data available. It's not going to have finished processing the data. Second, we're going to need to wrap up all of our state, because we're going to need to pass this from continuation to continuation. Because again, we're going to be returning, we're going to stop using the thread while we're waiting for the read and the connection to complete. And so, we're going to need to store our state somewhere. So here we'll create some state, and we just wrap everything up into a little structure. Next, we're going to establish the connection. We'll assume that our TCP library provides some overload of connect that returns, a future of a TCP connection. And then we'll attach to that a continuation. And in that continuation, we'll take that connection, and then we'll start a loop. And then in that loop, we'll basically do our read. And then for each read, we'll then go and actually go and process the data. And there's also this little do while, which is actually a pretty easy function to write. But Yeah, so is this as simple as the earlier example? I think it's pretty good, pretty easy to read, write, debug. Does anybody enjoy writing code like this? Anybody? Nobody's raising their hand. So when Gore gave this talk at CPPCon, I raised my hand sarcastically, and then I got picked on. So there's actually a bug in this code. Does anybody see what it is? Yeah. So in our original example, we returned that total. And in our new program, well, we don't seem to do that anywhere. So we have to attach here, we just need to add the right return statement in the right place. Does anybody want to take a guess as to where it needs to go? Okay, well, I'll give you the answer. It just needs to go on to the end. We need to attach yet another continuation that when we're done with this entire thing, we basically just return a future that contains all of the that contains the number of bytes that we read. All right, so this is problematic, right? Because this does give us better performance if we don't want to be blocking that thread for a long period of time when we don't have to. But this was rather difficult to write. We had that little bug there, and figuring out how to fix it was non-trivial if you didn't know the answer. And thankfully, Gore told me the answer. And finally, if you wanted to debug this is going to be a real pain in the butt to debug, because you get a stack. If let's say that something crashes inside of this very inner continuation here, right? You're going to get some kind of stack dump or crash dump, and in the stack you're just going to have this lambda name that's usually not very difficult to decipher, and you're going to figure out, well, which lambda was it? Where was the failure? What was the context in which it failed? So, all right, that's not very good. So maybe a state machine will be simpler. We can actually model this pretty easily as a state machine, right? We start, and then we go into our connecting state. We call TCP connect, and then that will either fail, or we'll start reading, and we'll read the data, and then when we're done reading the data, we'll enter the completed state, and we'll be done. And we can actually model this pretty easily in C++. We just need that data again, and we can wrap everything up in a class, and we have these nice member functions that map to each of the state transitions, and this is about as much code as our synchronous example. So that's nice and short, except that we have to actually implement all of those state transition functions, but that's not too hard. We've got the on connect here and the start, and we've got on read and on error and on complete. So now we've got 3 times as much code as our synchronous example. At least we'll get somewhat nice crash dumps when it crashes, and I'm sure it will. But still, this is not great. So what do we really want, right? What we really want is we want to write code that is this simple, but runs asynchronously. And so we can actually do that with the C++ coroutines proposal. So here is our synchronous example with some white space added in. And the white space is there so that I can fill in the changes that we're going to make. And now this is the asynchronous version that has roughly the same behavior as the continuation one that we had that was nested deeply and had lots of code. And just to highlight the changes that we made, we've changed the return type from int64t to stdfuture of int64t. We've added this co-await keyword, which we'll discuss, which basically says, suspend execution of this function until this operation completes, and then allow us to resume. And then we've turned the return keyword into the co-return keyword, and we'll also look at what that means. All right, so now let's dive in and see what this actually does. But to start with, what is a coroutine to begin with? Well, a coroutine is a generalization of a subroutine. Well, all right, what's a subroutine? Well, a subroutine is something that has 2 properties. It can be invoked by a caller, so you can call it, and it can return control back to its caller. So in C++, does anybody know what a subroutine looks like? Anybody? It's a function. So a function in C++ is basically a subroutine. A coroutine also has those properties, so you can also call a coroutine and it can return control back to its caller. But it has 2 additional properties. It can suspend its execution and return control back to its caller early. And then after it has suspended, it can be resumed. And basically when it resumes, it'll just resume where it left off and continue executing. So in C++, once this feature is added, both subroutines and coroutines, they're both going to be functions, and a function can be either one of these. And so to look at this table, So, in order to invoke a function or in order to invoke a subroutine, you just make a function call. And in order for it to return, you just return. And similarly, for a coroutine, you invoke it exactly the same way. And when it needs to return, it uses the co-return statement. And we want to suspend the coroutine, we use co-await. And we'll look at how to resume it in a little bit. So what makes a function a coroutine? Is this function a coroutine? If you just had this declaration, would you say, is this a coroutine? Anybody would say yes, raise your hand. Anybody say no? Okay, the correct answer is maybe. Whether a function is a coroutine or not is an implementation detail. It does not affect the type of the function. It doesn't affect the declaration. You can turn a function into a coroutine or turn it from a coroutine into a normal subroutine, and no caller will ever care. So it's entirely an implementation detail. So what makes a function a coroutine is basically that it does coroutine things. It either uses co-return or co-await or co-yield or some combination of these. So here's an example of two implementations of this compute value function. And on the left, we can see this is just a normal C++ function, a subroutine, and it calls std async to go and run on some background thread. And it'll run this lambda that'll just return 30, and then it'll return the future that's returned by std async. So this is a normal, C++ function, nothing fancy there. On this side is a roughly equivalent function that is a coroutine. And so it also uses std async to run something on a background thread, and then we pass it this lambda that it'll execute. And what this co-await will do is it will actually suspend execution, and it'll return the std future back to the caller at that point. And then when this completes, right, and when you call when this completes, this co-return will run to actually return that result to set the future. So both of these are two different implementations. If you had this first one, you could easily convert it into the second one, and no caller would ever care. They're exactly the same as far as the caller cares. So what does this co-await actually do? And I guess I should mention at this point, up until very recently, it was just await, and a long time ago it was _ await. It's now co-await. There was some concern that adding a keyword named await would, even if it was a contextual keyword, would potentially break code. So they decided that co-await and co-return and co-yield instead of the non-prefixed versions is preferable. All right, so let's say we have this co-await. So we co-await some expression and assign its result to something. What the compiler does is it transforms it into this code. So basically, we'll just create some named things that we can refer to the expression. And the first thing the compiler will do, it'll ask, are you ready? So do you already have the result that I want? And if it already has the result, then the compiler's not going to suspend the execution of the coroutine. It's just going to jump down here, and it'll call await resume to actually get the value back that it needs from that expression. If it's not ready, then it's going to call await suspend, which tells that thing, hey, I'm about to suspend. If you need to do anything before I do that, then go ahead and do those things. And then it's going to suspend. And what that means is that it's going to return control back to the caller as if the function had returned. The function, or its caller, or anything else really, is then able to resume this coroutine. And when it does so, it'll start executing right here, and it'll end up on the next line, and it'll call await resume to get whatever the value was. So we can see from that in order to await something, it has to define these three operations. It has to define await ready, which tells the implementation, okay, does it already have the value or not? It has to define await suspend, which is something that'll run just before the coroutine is actually suspended. And it has to have await resume, which is how it gets the value back out of the await expression when it's ready. So let's look at an awaitable type. So this is the simplest awaitable type, and this is actually in the standard library as part of the proposal, and it's suspend always. And what this does is it always suspends the coroutine. And so all it does is in its await ready function, it just returns false. I'm not ready, so suspend. And then it doesn't have to actually do anything in the await suspend or the await resume. So if we have a function that uses that, this coroutine here, when you call the coroutine, it'll print out this message, and then it'll suspend. And then when it's resumed by its caller, it'll then print out this message, and it'll complete. Another of the simple awaitable types is suspend never, and this one does not suspend. It's basically a no-op awaitable. And so it just returns true, yes, I'm ready, and then it does nothing else. And so if we have a function that makes use of this, it'll print out this message. It'll attempt to await this suspend never, which will say, nope, I'm ready, and then it'll immediately print out this message without actually suspending the coroutine. We'll see how this is useful later on. It may not appear immediately useful. So that's the first half. When a coroutine is executing, it uses co-await to suspend itself and return control back to its caller. So how does the caller resume a coroutine? Well, we have to look at what happens when you actually invoke a coroutine in the first place. Before we do that, what happens when you invoke a function? Well, the compiler goes and it establishes a stack frame for the function. The stack frame includes space for arguments, local variables, the return value, storage for volatile registers. Not all of these may need to actually be in memory. Some of them may be in registers. But basically, the compiler is going to use some memory on the stack to go and store this information that it needs. Similarly, it needs to store those things for a coroutine. And it does so by constructing a coroutine frame that contains space for all the parameters, all the local variables, selected temporaries, execution state for when the coroutine is suspended. So when you suspend the coroutine, it needs to go and store off the state of any registers that it might need when it is resumed. It needs to store off the instruction pointer so that when you resume it, it knows where to resume execution, and other related things. And finally, it needs to store the promise that is used to return a value or values back to the caller. And we'll take a look at that in more detail. So in general, this coroutine frame needs to be dynamically allocated. And that's because when you suspend a coroutine, the coroutine loses access to the stack. It's no longer on the stack. The function that it returns to could call something else that's going to go and use that stack space. So operator new is used. Basically, the compiler generates code that uses operator new to construct these coroutine frames, and that can be overloaded for specific coroutine types to allow customization if you need to, allocate from a pool or do some sort of custom allocation. Creation of this coroutine frame occurs just before the coroutine starts running. So just like creation of a stack frame for an ordinary function, you don't actually see that happen in your code. Creation of the coroutine frame, you don't actually see that in the code. It all happens behind the scenes. And then once the compiler has created the coroutine frame, it returns a handle to this coroutine frame to the caller of the coroutine so that it can access it. So what does that handle look like? Well, it's a special type in the standard library called coroutine handle. And there's two versions of this. The first one is for a void coroutine, so a coroutine that does not return a value back to its caller. And that provides most of the basic operations. And then the second one is a coroutine handle for any other type of promise. So this is a coroutine that actually does return something back to its caller. And it derives from the void specialization so that because it shares all those operations, then it provides a few extras. So if we look at what's in the void specialization, first, it's possible to have an empty coroutine handle. And it's basically represented by a coroutine handle that has a value of null. And so we can default construct a coroutine handle. We can construct it from a null pointer. We can assign a null pointer to it if we want to reset the coroutine handle. And then we can test it as a Boolean to see, does this coroutine handle actually refer to a coroutine or does it not? In this sense, a coroutine handle is really just a special kind of pointer that has a few special operations. And those operations are, first, we can actually convert to and from void star. This is useful because it allows us to pass this through to C APIs that take a function pointer and a context. So for example, most thread creation APIs work this way. And so you can actually pass these through to legacy APIs very easily. Second, it provides the function call operator and a resume function. And this is what the caller uses to actually resume the coroutine. So it just calls resume, and that will resume execution of the coroutine. It provides a destroy function, which actually destroys the coroutine. And we'll look at that in more detail. And then provides a done that tells you whether the coroutine has finished executing. In addition to those, the coroutine handle for promises that actually return a value, like it actually gives you access to the promise that you can, so you can set that value. All right, so with that, let's build a simple coroutine. So here is a little counter function. And basically this counter is just going to suspend every time through its loop. And then when it gets resumed, it's going to go and print out a message saying, hi, I was resumed, and this is the number of times I've been resumed so far. And so here's an example program that makes use of this. So you can see that it'll print out and it'll let you know, oh, I'm about to call the counter, and then it'll call the counter, and then it'll resume the counter twice, and then it'll print that it's done. And so ideally, what we'll see this print out is something like this. So we can see it'll print out, it's calling the counter, and then inside of the counter, it'll say the counter was called. The counter will then suspend. The main function will say, okay, I'm about to resume the counter. It'll resume it twice, and each time through the loop, it's going to print out this message. And then at the end, it's just going to print, okay, I'm done. So how do we build this? Well, we need to define that resumable thing type. So the return type of any coroutine needs to define a promise type, and this is the type that controls the interaction between the caller and the coroutine. And so we'll look at that in detail in a minute. Our resumable thing is going to store the coroutine handle that we talked about. It's going to be constructible from a coroutine handle. When this resumable thing gets destroyed, it's going to destroy the coroutine. And then we're going to define that resume function that's just going to call coroutine resume. In addition to these, we're going to need some boilerplate. So this resumable thing is going to act sort of like a unique putter that owns that coroutine. And so we give it a default constructor, but we delete the copy constructor and copy assignment operator. And we give it a move constructor and move assignment operator that do the same thing that unique putter's operations do. And then we need to define the promise type, and it needs a few operations. The first operation is getReturnObject. So getReturnObject is how the compiler actually constructs the resumable thing that it's going to return. And the reason this is part of the promise type is so that the reason that it's part of the promise type is so that you can actually take that the promise, get the coroutine handle from it, and return it back to the thing that you're going to return. So this allows us to actually call that constructor that we had that takes a coroutine handle. In addition, you need to have an initial suspend and a final suspend function, and we'll see how those get used. In this case, we're just going to say, nope, we don't need those to suspend. And then finally, for coroutines that don't actually return anything, they need to have a return void function, and this defines what gets done when the coroutine returns. So back to the example coroutine that uses this type. The compiler is going to go and generate a context type for this to hold all of that state that we talked about. So it's going to hold the promise, which is of that promise type that we just defined. It's going to hold I, the local variable. It's going to have the instruction pointer, so that when it suspends, it can save that state. And then it'll probably have some storage for registers, depending on how the compiler actually goes and implements this. And then the compiler is going to take our counter function, and it's going to inject some code into there for us. So at the beginning, it's going to go and construct an instance of that context. And then it's going to go and set the return value. So, this is conceptual, so this is wherever it needs to do to construct the return value. And it's going to construct it by basically calling this getReturnObject function that we defined. And then it's going to await on that initial suspend. And this initial suspend gives you the opportunity to suspend the coroutine before it even starts executing. Then it's going to enter the body of the coroutine, and it'll do whatever we need there. And then finally, at the very end, it'll define this final suspend label, and it'll call that final suspend function. And this allows you to suspend execution of the coroutine between the time that it returns and the time that it actually gets destroyed. Does this make sense? Are there any questions? You can feel free to interrupt me. All right. That's good. There's no questions. So this resumable thing, though, is not specific to this counter coroutine. And as an example of this, we can also use it to define a coroutine called named counter. And this one takes a name, And in addition to printing out the number of iterations, it'll print out its name. And we can use this in order to see that, like when we suspend execution, we can actually go do other arbitrary things. And so in this example, we're actually going to construct 2 instances of that coroutine, and then we're going to resume them in different orders, so that we can see that, okay, when we resume one and it returns control back, we can then resume another instance of it, and it'll return control back, and we can switch between them as needed. And so here's an example of how that output will look, and I've tried to color them in red and purple to show how they correspond. So now we can fill in that resume field. So when you want to resume a coroutine, you call that resume function on the handle for it. All right. So now what happens if we want to return something from a coroutine? So, that was all very interesting, but that, coroutine isn't particularly useful. What if we have something like our stood future example, where we actually want to return a future from the coroutine, and then we eventually want to provide that future with a value? Well, we just use co-return. That was simple. Okay. Well, there's 2 interesting things about that. First, why is it co-return instead of just return? And second, and kind of the answer to that first part is, well, that result is not a future of int. That's an int. And furthermore, you can't convert an int into a future of int. There's no constructor that would let you do that. So if we look back at that promise type, if we want to return a value instead of returning void, we need to define a function named return value. And this takes some type of thing. You can define different overloads of this if you want to be able to return different types of things. It could be a template. And so that return void gets called for a co-return when there's no argument, or it gets called when you reach the end of a coroutine, just like what would happen with a normal function. And then return value gets called whenever you return something that actually has an object from the or a value from the coroutine. So if we'll reduce that get value to something a little simpler, just so that we don't have to deal with the complexities of stood future here. So here's a sample coroutine that we want to implement. And what it's going to do is, when you call it, it's going to await on suspend always, so it'll suspend immediately. And then when it gets resumed, it will return 30 back to its caller. So let's go and make the changes required to resumable thing to make this happen. Nope, that's not what we're going to do yet. So we want to look at what happens when we actually do that co-return. And basically, what the compiler is going to do is it's just going to transform that into a call to that return value with whatever the argument was to the co-return statement. And then it's going to go to the final suspend label. And obviously that's a no-op here, but you could have these all over the place inside of the coroutine, and so it'll jump to that end. And then it'll await on whatever that final suspend was. All right, so now we need to update our promise type in order to support this. So this was the stuff that we had before. So we're going to need to add a value. So we're going to need to store the value in there somehow. We're going to need to define that return value function, which is quite simple. We're just going to assign that member variable to the argument. And then finally, we need to define that get function so that in the main function, it can actually get the value that was returned. And so here, we just get the promise associated with the coroutine and return the value. So if we walk through the example that uses this, we'll see that main will print that it's calling get value. It'll make the call to get value. Get value will suspend, and then main should print that it's resuming get value. Get value will print, okay, it's been resumed, and it'll actually return 30. And then main will print that the value was 7,059,560, which is exactly what we returned, so that's good. So what happened here? Well, we have to talk a little bit about Coroutine Lifetime. So the first part is easy. A coroutine comes into existence when it gets called. So when you call the coroutine, the compiler goes and it constructs that coroutine frame for it. All that happens automatically as soon as the coroutine is called. The coroutine is destroyed when the final suspend is resumed, or when destroy is called on the coroutine handle, whichever happens first. So if we look back at our get value, we see that it's going to set the return value, it's going to jump to the final suspend label, and then it's going to await on this final suspend. And our final suspend was suspend never, so it's not going to suspend at all, it's just going to return immediately. And then here at the end, it's going to go and destroy, the compiler-generated code will go and destroy that, the coroutine context. So if we look back at our promise type, does anybody know how we can fix this so that it doesn't get destroyed? Yes?
Suspend always?
Yes, we just need to change it to suspend always. So this will cause it so that in that final suspend, it'll actually block there. Well, it won't block. It will stop there. It will suspend execution of the coroutine, and it'll return control back to the caller. And so when we make that change, yes, the promise still exists, and so we can call get on it, and we can get the correct value 30. So then, at what point here does the coroutine actually get destroyed? Well, remember that in our resumable thing destructor, we actually called coroutine destroy, and so that will destroy the coroutine. So how does coroutine destruction work? Well, it'll destroy all of the local variables. So here's an example. I have a little print when destroyed type. I don't have the definition here, but basically it just prints in its destructor when the objects get destroyed. And so you can see here that main calls get value. It'll resume get value. And then at the end here, when main destroys the resumable thing, it'll destroy B, and then it'll destroy A in that order, because, again, local variables get destroyed in reverse order. But what happens if we don't get to the end of the coroutine? So, for example, what happens if we fail to resume the coroutine? So the coroutine is stuck here, suspended on the suspend always, and this resumable thing goes out of scope, and so its destructor gets called. Well, basically, all of the local variables that were constructed already are going to get destroyed. So it's just like if you had returned early out of a function. It's going to destroy all those local variables. It's not going to destroy any local variables that hadn't yet been constructed. So as a recap, a coroutine is destroyed when the final suspend is resumed, or when you actually call destroy, whichever happens first. And when a coroutine is destroyed, it cleans up all the local variables, but only those that were initialized prior to the last suspension point that was reached. So again, this is where we're basically at the same place with the coroutine, the comparison. Okay, well, those types aren't still particularly useful, so let's go and implement something that's actually useful. Let's look at stood future. So who thinks it's going to be easy for us to implement, basically make stood future work well with this new coroutine feature? Not very many people. Okay, well, let's see. So future is actually a good example because we need to implement both sides of this. We need to implement both the ability to await on a future and the ability to have the future be the type of the coroutine. So let's start by doing that second piece. Let's start by enabling future to be the type of a coroutine. And in order to do that, we need to implement the promise type for it. That's it. So we can do that. We can start by cracking open our future header. And we'll just add a promise type to it. Oh no, let's actually not do that because you guys shouldn't be cracking open the standard library headers. So it turns out there's another way to add or define the promise type. And this is especially useful for if you have existing libraries that you don't want to hack up or modify, or if you have some C types that you want to wrap up and use as coroutine types. And to do that, there's a second library type. So we already saw the coroutine handle. The second type is coroutine traits. And coroutine traits allows you to customize how the promise type is found. So the primary template, all it does is it says, look, if coroutine traits was not specialized for the type, then just go and find the promise type as in the scope of the return type. But we can specialize this for any type we want. The arguments is for extra customization. We're not going to look at that today. You can read the specification if you'd like the details on that. But so here we're going to go and implement promise type for future as an extension, just using a specialization of coroutine traits. So in there, we're going to need to store the promise, which the future uses in order to, or which is used with future in order to return the value. we're going to need to define that getReturnObject function. And so stdPromise has a getFuture function that returns the stdFuture associated with it. We need the initial and final suspend, and we don't actually need to suspend either of those. For the final suspend, we don't actually care when the coroutine is destroyed, because stdPromise dynamically allocates its state and it's shared with the future, so we don't need to worry about when the promise goes out of existence. We need to define return value, which is quite easy. We basically just call setValue on the promise. And in addition, we need to define one more function called setException. And what setException does is basically if in the coroutine, while we're awaiting, if an exception is thrown, if this setException function exists in the promise type, it will get called instead of allowing the exception to propagate. And this allows us to call setException on the promise so that we can take that exception, wrap it up, and then transport it over to whoever's going to call get on the future. So that's it. Now we can actually define coroutines that return a stdFuture. Was that easier than everybody was expecting? I hope? Okay. So now what about the await side? Well, once again, we can open up our future header and crack open the future class and start defining some nope, we're not going to do that. So again, we can also customize this without modifying the future type. And to do that, basically, we're allowed to define these as non-member functions that take whatever the coroutine type is here. So here, in this case, it's future of t. So we can define awaitReady by calling isReady on the future. We can call awaitSuspend, and what awaitSuspend will do is it'll just say, okay, well, when the future when the future is ready, then continue, and in the continuation, resume the coroutine. And then in awaitResume, we just call get to get the result of the future. Does this make sense? Okay. I'm not sure if that's yes or no. So I have to admit, I have cheated a little bit here because isReady and then are not actually part of stdFuture. They are part of stdExperimentalFuture, which is the new future. These were sadly omitted from the original specification, which made future not particularly useful for actual programming. And if you want to look at that, I have a note or a comment in the slide notes. You can go and find the actual paper that proposes that. So that's that. So between those two, in 2 slides worth of code of fairly large font, we were able to make future both awaitable and into a coroutine type. So you can define these for basically any type that you have that you want to be able to await on or define a coroutine in terms of. So another feature of coroutines is the ability to yield. So what if we want to suspend a coroutine, not return, but we want to suspend a coroutine, but also provide a value back to the caller, and then allow the coroutine to be resumed again, potentially to yield another value back or to return at that point? Why is this useful? Well, the obvious example for this is generators. So generator is something where every time you call into it, it'll yield you a new value. So here is a function, or a coroutine function, that called integers. It takes a first and a last, and it'll iterate from that first one to the last one, and it'll yield all of the integers in sequence. And so here is a program that uses it. It calls integers, and this should hopefully print out the integers 1 through 5 in order. There's no magic in this range for loop here, like there's no coroutine specific stuff. We could replace it with a normal for loop that operates on iterators. And the way this works is we're going to actually define that iterator type, and we're going to define that begin and end function. So what does co-yield do? Co-yield basically just calls promise.yieldValue, so this is yet another function we can define on the promise, and then it awaits on the result of that. So if we want to go and implement the promise type for our generator, Our getReturn object is exactly the same as we had before. Basically, it just gets the coroutine handle from the promise, and then it goes and constructs an int generator from that. It's going to store a pointer to the current element that it has returned. It's always going to suspend at the beginning. This way, it does not actually produce a value until you call into it for the first time to get the first value. And then it's always going to suspend at the end. And then our yield value is quite simple. We're just going to store in the current, we're going to store a pointer to the current, the value that we're yielding, and then we're going to suspend. So I'll note that in this case, for int, it doesn't really matter that we're returning a pointer or that we're storing a pointer instead of a value. But if we had a large object, it would potentially be more efficient. It is guaranteed that whatever this value is will not go out of scope until after the coroutine is resumed again. So it's guaranteed to be in scope for long enough because, again, when the coroutine suspends, it needs to stash off all of its state, and so it's going to have that state stored until it's resumed again. So then we need to implement our begin and end functions of our generator. And for these, quite straightforward. In the begin, we're going to resume the coroutine, and if it's not done, if it still has values to produce, if it's not done, then it's going to return an iterator that holds that coroutine. And if it is done, then we're going to return the end iterator, and the end iterator is just a default constructed thing. And this will allow us to basically compare the beginning and end. In defining the iterator type, this is obviously going to be an input iterator because we can't go backwards in time in execution of the generator. So the iterator will just store the coroutine. In our operator ++, it'll resume the coroutine. And if the coroutine is done, then it'll reset it so that it compares equal to the end iterator. Otherwise, it'll return the iterator. And then when we dereference it, we're just going to get whatever the current value was that was produced. So I've omitted all of the boilerplate from this example, like the equality operator and inequality operator constructors, things like that. But if you want, there's a generator header in the Visual C++ update that actually defines this full type, and it's basically exactly like this. So if we go back to the integers type, that's basically how it works. Each time through the loop, it's going to call co-yield, which will call that yield value. It'll set the value, it'll then suspend, and then we will have the value here in the loop that we can print out. Are there any questions about that? Yes?
Is the compiler able to optimize everything and make it like a normal for loop?
Yes. So the question is the compiler able to optimize everything? Yes, ideally. So the compiler can, always has the opportunity, well, let me rephrase. The compiler is always allowed to optimize everything. And in this case, yes, the compiler, in theory, should be able to inline that call into the generator if it makes sense, or do other optimizations there. We are still, so in the Visual C++ implementation, we're still working on, implementing things, making things optimizer friendly. But yes, ideally, the compiler should be able to optimize that just as it would, normal function calls or other things. In fact, it would probably be easier for it to optimize coroutine code than like the explicit continuation passing code that we had before, because the compiler actually has the context of what's going on. It doesn't have 12 layers of library functions to go and try and optimize through. All right, so with that, we've got our final table here. So with the coroutine, you can call them just like normal functions. They return using co-return, which doesn't actually return the value directly, but it sets the value in the promise. You can suspend the coroutine using co-await or co-yield, which is just a special form of co-await that lets you yield a value. And the caller or anyone else can resume the coroutine by calling resume on the coroutine handle. If you're using Visual C++ and you have, we just released the first update for Visual C++ 2015, you can actually use this. There's no co-prefix on any of these yet, but you could define macros to make that work, which is what I ended up doing for testing here. Some of the required function signatures are a bit different, but you can look at the examples in the headers. Good examples to look at are std future, which we do have basically almost the exact same code as what I showed in here is in our actual headers, and then the generator implementation on how to yield things. We should, I expect, have things fixed up to match the current specification for the second update, but then, the spec will probably have moved on to, more changes. So with the coroutine control flow, the co-return just calls return value or return void if we use the void form. And then it goes to the final suspend label, giving us the opportunity to suspend the coroutine if we need. Co-await will check and it'll wait, or it'll see is the coroutine already ready, and if it is, then it will resume immediately. Otherwise, it will suspend, and then when it's resumed, it will acquire the value. And then co-yield is just the special form of co-await that allows you to yield a value. So to finish up, these were the design principles that were used during the design of this proposal. So the first was that we wanted it to be scalable. So basically, we wanted to enable you to have billions of these coroutines, concurrently ready to execute, concurrently sitting there at the same time. This was one of the reasons that we ended up with the current stackless approach, where you can only yield from within the body of the coroutine itself, not from some function that it is called. We wanted them to be efficient, so we wanted the suspend and resume operations to be comparable in cost to function call overhead. We wanted it to be open-ended so that library designers can go and you can develop coroutine libraries exposing various high-level semantics. So we saw the generators and tasks stood future, and you can also implement Go routines, and there's all sorts of design patterns that you can implement on top of this. So those types, coroutine traits and coroutine handle, they're very low level, right? Coroutine handle is basically just a raw pointer with a few extra operations, but you can very easily build things on top of these. We wanted to enable you to have seamless interaction with existing facilities. So this is, like we saw, you could easily adapt stood future, assuming it had is ready and then members, so that it would be able to work with this new feature. You can similarly do things with almost any other library types. And then finally, we wanted it to be usable. I didn't show examples of this, but in environments where exceptions are forbidden or not available. So this is either your colleagues just hate exceptions and they think returning status codes are the best, or maybe you're in kernel mode code or in really old legacy code that you want to start using this and you can't use exceptions for those reasons. Oops. So a couple references to look at. So N4402 is the ISO C++, the most recent version of the easy-to-read description of the resumable functions feature. The second paper is the actual wording, so this is the actual proposal that's being proposed for standardization, the current state of it. And then my colleague, Gor Nishanov, has given 2 talks at CPPCon 2014 and 2015, in which he gives a much more animated and interesting introduction to these. And so I highly recommend that you go and watch those if you're interested in more information. And with that, are there any questions? Yes. And there's a microphone there too, or you can either way.
So this looks a hell like the C#.NET stuff, and which there's the basis for Link and RX. And so what's your take? Is this also considered is this the beginning to bring libraries like that to C++ world, or is it intended for that also?
This is intended to enable you to implement all sorts of patterns in C++ that you can't easily implement today. So for example, in C#, they have generators, they have the yield, I believe it is, and then and I believe that's where we got this term from. And then of course they have async functions, which are very similar to the model of what we've shown with stood future here. I know that the C# await was one of the original implementations that was looked at when this was being done for C++. And so, yes, that was, I guess part of the interesting thing. Gor has done great work to generalize this extensively to make it, much more applicable to many different design patterns. So, yes, ideally we should be able to implement all sorts of interesting things with this. Yes?
Are there any plans of creating some possible way to automatically apply await keyword to some functions? For example, to use this function in standard algorithms and other already existing functions?
Are there already...
Well, for example, we have a standard algorithm for each that applies some function to some range. And we cannot use this function right now to a coroutine because it returns well, no. Okay, not for each, for example, accumulate. We calculate a sum of a result of some function applied to each element of a range. And it would be great if we could use it on some resumable function, and it will create us another awaitable function.
I see. So like an awaitable for each that will await each operation as it's going along.
We don't want to create a new function for this because...
Right. There's nothing in there today. I'd have to talk to Gore about that. I don't know off the top of my head. I'll have to suspend my answer to that and resume after I get some more information.
Okay, thank you.
Yes.
Can we go back to the first example when we saw the co-await for the first time? I just have some questions there.
Maybe.
Just to understand what's happening. That's a lot. Well.
I may have gone too far. One moment.
Okay, so let me, we have a function that returns a future. So
Here we go.
What's happening underneath, we return immediately, and then we start executing the coroutine handle asynchronously. Am I correct in that view?
Could you repeat that?
Yeah, well, we return we have the handle returns a future, basically, in our first example.
Yes.
So it returns immediately, and then the handle starts to be executed asynchronously. Am I correct in that assumption?
So in our stood future example?
Yes.
So in the stood future example, what will happen is you'll be able to return a stood future immediately that is bound to whatever the final result is when the coroutine gets to that coroutine statement. And the way that works is when you co-await on the call to stood async, right? So stood async will return a future. And then in the await suspend in there, we attached the remainder of the coroutine to that as the continuation of that future. So when that call to async finished executing, it would go and resume the coroutine at that point in whatever context that happens.
Okay. Okay, yeah, I was trying to figure out which threads were involved and what was happening.
Got it, yeah. So in that case, the coroutine would be resumed in a different context than it was suspended, right? So it would be suspended, maybe on the UI thread if that's where you were running, and then it would be resumed as a continuation of the task that you ran using stood async.
Okay, thanks.
Go over here. Oh, okay, sure.
On one of the last slides, you said it is stackless.
Yeah.
You don't have to get it slide, no. Is there any chance that this can be implemented heapless for systems without a heap? I saw a big news somewhere.
Yes, so you can actually overload operator new or override. I forget which term is correct for operator new. But you can actually overload that for the particular promise type or the particular coroutine type. And so you can implement that to have it allocate however you need it to do. So if you want to allocate from a memory pool or from some static block of storage, you can do that.
But it would be nice if it could be part of that future. So, don't
Yeah, so you absolutely could do that.
let's hope someone does.
Yeah, and in the, I mean, yeah, you'd have to, in that case, you would actually have to modify the promise type, the std promise, in order to support that, but that's certainly an option that you could do.
Hi, so in the first example that you showed with this TCP/IP listener, essentially, you just added a few co-await and co-return, and then you claim that's it.
Yes.
And then you spend like another hour explaining what else needs to be implemented. So I got a bit confused on what do I actually need to implement to get this first example running and what is already there.
Yep, so all of the stuff after that was what library developers need to go and do in order to implement, basically make their libraries work with the new coroutines feature. But you as, an end user or a normal developer, I guess, an application developer, doesn't need to generally write any of that code, right? Like you might if you have a library that you want to start using this with that doesn't yet support it, but otherwise you can easily go and, just use types as needed.
Okay, cool.
Yeah. So my intent wasn't that, look, you just have to do this, and all these other things. It was, most developers should only have to do that one thing, and then, library developers have a little bit of work, but hopefully it's not too much. Like we saw, std future fits in 2 slides. And that was the actual std future code from our implementation that we ship, almost. Yep. I don't know what.
You accepted a standard string into one of your coroutines. How is that copied into the context? Is it copy constructed in, or can you control the
Yes. So how does how do the function arguments get stored into the context? Yes. Each function argument will get moved into the from the wherever the parameter was into the coroutine context using std move. I am not entirely sure what happens if you don't use an argument, like if there's a std string that is never used. In that case, maybe the compiler can avoid the move. I'm not entirely sure on that.
Similarly with local variables, every time you suspend, are you copy constructing back into storage?
No. So for local variables, they will actually just exist as part of that the context, right? They'll never exist anywhere else. I think we have time for one more question, if anybody's got one more question. All right, we've got one more question.
I have a question about iterators produced by a generator class. What happens if we copy an iterator and then move a couple steps forward and then dereference that iterator?
Yep, so it's only an input iterator, not a forward iterator, so you're only allowed to iterate over it once. And I think the rules for input iterators are that you can make copies, but once you advance one copy, all the other copies you're not allowed to touch anymore.
So it's great.
All right, well, thank you everyone for coming. I'm happy to answer any questions later. But